The second talk of today is by Abhinav Prem from Princeton University, and he's gonna tell us about many-body dynamics in constrained systems. Abhinav, please go ahead.
Thanks a lot, Hassan, for the invitation. I'll keep my video off just because the bandwidth is a bit low here. It keeps dropping. Okay, so yeah, today I'll tell you a little bit about some work that I did with people at Princeton based on this work that's on the archive, and then some forthcoming work if I have time, which hopefully I will post this month. And the basic theme is about sort of the absence of thermalization in systems with constrained Hilbert spaces. So given the recent advances in experiment, we can now study, there's been a lot of advance in studying the dynamics of isolated systems. Experimentalists have a lot of control in creating interesting initial states and then studying their dynamics. And so there's been a lot of interest in the question of quantum thermalization, which is the question of how and whether a closed quantum system reaches thermal equilibrium. And sort of in the process of looking into these kinds of questions, people have found many interesting non-equilibrium phenomena, such as what Mohammed was talking about. But then, and that's in open systems, but even in closed systems, there are interesting, many interesting new phases that can be realized, such as time crystals or many-body localized phases, etc. And so the general question that one is interested in is whether or not a closed interacting system reaches thermalization. Okay, so here's sort of the rough outline for the talk today. I'll start with a brief review of ergodicity and its breaking in isolated systems. I'll say something about quantum many-body scars, which is sort of a burgeoning field. And then I'll discuss sort of the work that we did, which is the idea of Krylov-restricted thermalization in a physically relevant system. And then if there's any time, I'll say something about some recent work that we've been doing on spectral statistics and constrained random unitary circuits. Okay. And also please feel free to interrupt and ask any questions. Okay. So in an isolated quantum system, we say that a system is ergodic if any initial state that you start with evolves into a thermal state. And you can probe this by looking at the reduced density matrix of the system. So for a thermal state, the reduced density matrix on region A is just the Gibbs density matrix on that subsystem. So we can calculate the entanglement entropy, the one-Neumann entropy. And for an ergodic system, the entanglement entropy of simple initial states, such as product states, is expected to grow linearly with time. And this has been probed numerically in many systems. And so an important development in the field of thermalization is the concept of eigenstate, is the ETH, which is the Eigenstate Thermalization Hypothesis. And ETH is basically a statement about thermalization at the level of individual eigenstates. It states that each eigenstate implicitly contains a thermal state. And here we're interested in eigenstates which are in the middle of the spectrum, of the many-body spectrum. And so according to ETH, if you compute the expectation value of local observables, then each eigenstate behaves as a thermal ensemble. And the entanglement entropy of states in the middle of the spectrum is expected to obey a volume law. It grows as the log of the Hilbert space dimension. And so it obeys a volume law. And this is different from the behavior of ground states, which obey an area law. Sorry. Okay. So ETH is now typically divided into the two forms of it. There's a strong version of ETH, which states that all eigenstates at a finite energy density satisfy ETH. And we expect that Hamiltonians that don't have some extensive number of conserved quantities satisfy strong ETH. And then there's weak ETH, and this is a statement that typical eigenstates at finite energy density satisfy ETH. So weak ETH allows for the possibility of a measure zero set of non-thermal eigenstates. And in fact, weak ETH is enough to prevent the system from thermalizing, because you can always pick some initial state which fails to thermalize. Now, typically we expect that ETH is violated in two kinds of systems. So the first are fairly simple and familiar, which are integrable systems. And these have an extensive set of conservation laws which impose constraints. And these constraints prevent the system from thermalizing. It is thermalized to the generalized Gibbs ensemble. But integrability is special, and it only exists at particular points in parameter space, and it's unstable to arbitrary perturbations. A more stable phase of matter which violates ETH is the many-body localized phase, and this is these kinds of systems emerge in generic interacting systems with disorder, and these evade thermalization many-body localized systems have emergent integrability. They show a slow growth of entanglement entropy. It grows logarithmically and not linearly. And in these systems, the system there's a memory of initial conditions for arbitrary long times. I should say that there's still sort of an open question about many-body localization with translation invariance in the absence of disorder. So the current paradigm for closed interacting, possibly disordered quantum systems is that the system either thermalizes, which means it can act as a path for itself, or it's many-body localized. And in a thermalizing system, you get extensive entanglement, rapid spread of energy, and the correlations decay rapidly. Whereas in many-body localized phase, you have boundary entanglement, the system retains a memory of initial conditions, you have emergent integrability, and then many exotic phenomena such as localization protective quantum order, such as you can have topological order for states in the middle of the spectrum. And so sort of an obvious question is there anything beyond this paradigm? Or in other words, can you have ETH in most of the system, but then have some states which in the middle of the spectrum which don't obey ETH? And so one possibility is that there are many body analogs of single particle quantum chaos. So sort of if you have unstable periodic orbits in a classical system and you quantize it, then you see these scar states, single particle scar states, which have been known since the work by Heller. And so recently there's been a lot of progress on this front. Of course, the problem is difficult because we're trying to ask questions about states in the middle of the spectrum and we don't have a lot of analytical tools there. But there's been a lot of progress in this direction, which is sort of spurred mostly by this experimental observation of many body revivals in a physical system, and then also the discovery of exact quantum many-body scars in a non-integrable model in the AKLT model. And then this has sort of led to the rapidly developing field of many-body scar states. So that's sort of the general setup. Let me say something about many-body scars. I'm assuming most people are familiar with it. So many-body scar states are special non-thermal states which are embedded in the middle of a system which is otherwise thermal. So most of the states in the Hilbert space obey ETH in the middle of the spectrum, but then you have some special states in the middle of the spectrum which have an area law entanglement, and these violate ETH. So these systems with these many-body scars violate strong ETH because you have a measure zero set of states which fail to thermalize. And these kind of scar states are the ones that underlie many-body revivals that have been seen in experiment. So one example of these scar states occurs in the spin 1 AKLT Hamiltonian. So this is just a spin 1 chain. You can write it in terms of projectors or in the more familiar form. And this model is non-integrable. You can calculate its level statistics, and it shows Wigner-Dyson level statistics. But in work that was done here at Princeton by Andrei Berdnevig and his student Sanjay, they were able to find analytically a tower of exact states which violate strong ETH. And so they find these outlying states in the middle of the spectrum which fail to thermalize. Concurrently, there was an experiment at Harvard where in a chain of Rydberg atoms where they considered, they considered a chain of Rydberg atoms and they initialized the system in an AL state. So you have states which are in the Rydberg state alternating with states which are in the ground state. And they found surprisingly that in the system, which is a thermalizing system, there were coherent oscillations. And this is sort of very unexpected because again, generically in a many-body system, which thermalizes, you would expect that all states obey ETH and thermalize at long times. Okay. So by now, again, there's been a theoretical explanation of these many-body revivals in this system, and there's an effective PXP model that has been proposed. So this is just a spin-a-half chain in one dimension, and the Hamiltonian is just given by, it's just a ferromagnet with projectors, which disallow configurations with two states being in the excited state. And again, this model, similar to the AKLT model, is non-integrable. There's Wigner-Dyson level statistics, but they found that if you quench the system starting from the nil state and can compute its fidelity with the initial state. So you start in the nil state, evolve with the PXP Hamiltonian, and then compute the overlap with the initial state, you see these oscillations. Unlike in the AKLT model, here these oscillations are not perfect, so the fidelity decreases with time. So these scar states are imperfect. And the eigenstate properties of the model also show evidence of these kind of many-body scars. Again, you see these outlying states which have approximately equally spaced eigenvalues, and these are the states that are responsible for these coherent oscillations that are seen. And again, in contrast with the AKLT model here, the scars are imperfect, and it has to do with the fact, it's related to the fact that these eigenvalues are only approximately equally spaced. There's not an exact tower of states. So one theoretical proposal by Shirayashi and Mori for sort of generically constructing scar states is the following. It's a way to embed any states that you like into some ergodic Hamiltonian. So if you take some Hamiltonian of this form, so you have some local HI, and then you just have some projectors acting on it on either side, and then some other Hamiltonian H tilde, which can be arbitrary, except that you require that it commutes with all of the projectors, and you choose the projectors such that they annihilate the states that you want to embed. So if you can satisfy these two conditions, then the Hamiltonian commutes with the sum of all of the projectors. And so then the Hamiltonian becomes block diagonal, where you have this target subspace, which is just spanned by all the target states that you wanted to embed into the Hamiltonian, and then an orthogonal subspace. And so using this construction, you can just construct a Hamiltonian which has some ergodic subspace and then a target space which has into which you can embed whatever states that you like. And so this has now been used to take something like the toric code model, and you can embed its ground state into the middle of an interacting ergodic system. So this suggests sort of an alternate approach to quantum scars, and explanation for a possible explanation for the PXP model also. So suppose you had a Hamiltonian and the Hilbert space was decomposed had this block structure where you had an integrable subsector, so it's tridiagonal, and then you have a completely mixed random matrix, for example, or a thermal subspace. So this kind of a system, if you initialize states in the integrable sector, they would never leave that subspace, and then you would see effectively integrable dynamics. You can also have systems which have some dynamical symmetry, so such as this happens in the Hubbard model with eta pairing, and here again you can have this exact tower of states which are equally spaced, and you would get zero energy. You can start with any eigenstate, and then you can construct a tower of exact states and get scar states that way. And the PXP model is approximately of this form, where you have some thermal subspace and an integral subspace, but then they're connected by some sparse off-diagonal matrices. And it's been proposed that if you tune the PXP model away, you can sort of tune these off-diagonal couplings to zero, and then you would see perfect revivals in that model that's constructed that way. So this kind of fracture of the Hilbert space into these dynamically disconnected subspace happens pretty naturally in systems with fractonic constraints. And so kind of motivated by that, we looked at this Hamiltonian. So this was the model that we studied. And this is the minimal center of mass preserving model in one dimension. So you have fermions in one dimension, and there's no hopping term, there's no single particle hopping term, you just have pair hopping. So the only allowed moves are of the form two particles hop, so two particles from the middle can hop, sorry, two particles from the middle can hop out another way. So this model preserves center of mass. Yeah, okay. Right, so this model is a minimum pair hopping model, and you don't have any single particle hopping allowed, and this model commutes with the center of mass operator, which is essentially related to the dipole moment operator. And this, with translation variance with periodic boundary conditions, this model has a Q-fold degeneracy. And so just let me give you a couple of motivations for why we wanted to study the model. So again, it preserves center of mass, which is related to dipole moment, and then these, so that's sort of the underlying phenomenology that lies behind these fractonic systems, which are systems which have excitations with no mobility, or particles that can only move along lines or planes in higher dimensions. And this is, as proposed by Michael Prudko, in these models, in systems that have dipole moment conservation or higher moment conservation, you naturally get these fractonic excitations. And in higher dimensions, it was argued that these systems have slow dynamics, glossy dynamics, despite being translation invariant. And so the model that we study is sort of a natural analog of this, but in one dimension. Another way of getting this pair hopping model is actually from the quantum Hall effect, and this might be familiar to a lot of people. So if you just take the quantum Hall system and you put it on a thin cylinder and you take the limit of one of the lengths going to 0, because you have translation invariance in both directions, translation invariance in sort of the small side essentially becomes center of mass along the chain, because because the single particle orbitals are basically Gaussians that are centered along x, and so the translation invariance along y becomes center of mass along x. And so then if you pick any translation invariant interaction and you project it onto a Landau level, that translation invariant interaction in the limit of a thin cylinder becomes necessarily preserved center of mass. And so all interactions in the thin cylinder limit are of this form, where J1 plus J2 has to equal J3 plus J4. And so to the lowest order, you get some nearest neighbor interactions, but the first non-trivial dynamical term, hopping term you get is exactly the pair hopping model. Another and perhaps the most experimentally relevant way of getting the pair hopping model is if you just consider interacting spinless fermions in a strong electric field. And so this is just an interacting version of the block or Stark localization problem. The non-interacting problem gives you the familiar Wannier-Stark localization. With interactions, this model has been proposed as a platform for translation invariant MBL, because you see slow dynamics. But if you just study this model with interactions in the limit of an infinitely strong electric field, you'll notice that this term, the electric field term, is exactly the center of mass term. And so in the limit of an infinitely strong electric field, you exactly conserve the center of mass. You can do better than that. You just basically do Schrieffer-Wolff transformation, so degenerate perturbation theory. And again, the lowest order non-trivial sort of dynamical term that you generate is this hopping term, pair hopping model. Okay. So we'll just now focus on the pair hopping model and study what its features are. And just to connect it a little better with this fractonic phenomenology, we can introduce composite degrees of freedom. So I just identify a 0, 1 with an upspin, a 1, 0 with a downspin, and then 2 occupancies on neighboring sites with a plus charge, and then 2 neighboring unoccupied sites with a minus charge. So this is just a relabeling of the Hilbert space. But once you do this, you can translate the dynamical rules of the Hamiltonian, and they essentially become that spins are allowed to move freely. But then if you have a dipole, so a plus or minus next to one another, that's allowed to move left or right depending on what spin it has next to us. So if it has a downspin next to it, it's allowed to move left. And then analogously for the oppositely charged dipole. But if you have a single charge next to a downspin and an upspin, it can only move by emitting a dipole. So I had a single plus, and then this becomes a plus minus plus. So this reminds one of fractonic phenomenology, where you have a charge that can only move by emitting dipoles. And this, I should say, is at half filling. Okay, but the interesting feature of this Hamiltonian, or the Hilbert space under these rules, is that you get Hilbert space fracture. So let me define a Krylov subspace generated by some root state, just as the span of the Hamiltonian acting on that state. So I start with some state psi, and I just hit it with the Hamiltonian infinitely many times, and by definition, this generates a closed subspace. And we'll be interested in the dynamics of root states, which are product states, which are the ones that are experimentally relevant or experimentally accessible easily. Now, for a generic non-integrable model, which doesn't have any symmetries, we'd expect that if you pick any product state and you hit it with the Hamiltonian, you generate the entire Hilbert space. So the Krylov subspace generated by any product state should span the entire Hilbert space. If you have some symmetries, then the Hilbert space is a block diagonal with respect to those symmetries. But if you pick any product state with some, which is an eigenstate of the symmetry, then you expect that the subspace generated by that is the entire Hilbert space restricted to that symmetry sector. So you should generate all states which carry the same quantum numbers. But for the pair hopping model, actually, what you find is that even within the same symmetry sector, which is charge and dipole moment in this case, you get dynamically disconnected Krylov subspaces. And so the different subspaces here are not distinguished by some symmetry quantum numbers. There are distinguished by some non-local operators, but they're not distinguished by some by symmetry quantum numbers in the usual way. And so this is what we call Hilbert space fracture, where you have a Hilbert space that's broken into different blocks, but these are not distinguished by any symmetry quantum numbers. And the different subspaces in this model show very different properties, as I'll now discuss. The simplest ones are one-dimensional subspaces. So you have these frozen states. So if you consider two pluses, two minuses, and then these alternate. The Hamiltonian just acts trivially on this. So it's a zero energy eigenstate of the system. And in fact, you can show, as it was done in these papers, that in any model with center of mass or dipole moment conserved, there are exponentially many such frozen configurations within a given within a given charge and center of mass sector or dipole moment sector. And once you have these one-dimensional or frozen subspaces, you can systematically construct finite-dimensional subspaces from these just by embedding, for example, an up and a down spin. And so the only non-trivial action within the subspace is that the spins can flip, but the rest of the state is frozen. So those are sort of how you construct finite-dimensional subspaces, frozen subspaces in this model. And so this has a consequence, of course. So in the absence of one of the consequences is that in the absence of fracture, you'd expect that the bipartite entanglement entropy just evaluates to the page value, and that's just the average bipartite entanglement entropy of states in the Hilbert space. So this would just be L over 2 log 2. But for systems with a fractured Hilbert space, you actually get a smaller late time bipartite entanglement entropy, and it actually just evaluates to the Hilbert space dimension of half the system size, but of the Krylov subspace. So here dk is the dimension of the Krylov subspace that you get starting from the root state. And so the bipartite entanglement entropy evaluates to the page value within that subspace and not within the entire Hilbert space. And so this constitutes a violation of strong ETH with respect to the full Hilbert space. But besides these finite dimensional Hilbert Krylov subspaces, there are also infinite dimensional subspaces. And for those, you can ask some interesting questions. So one of those is, for a large subspace, by which I mean a subspace whose dimension goes to infinity, as L goes to infinity, can you have strong ETH violation? So ETH violation within a subspace and not just within the entire Hilbert space. And so this happens in this model. Sanjay, Andre, and Nicola showed that when you study this model at 1/3 filling, there's a subspace which maps exactly onto the BXP model. And the BXP model, of course, as we know, violates strong ETH. But in this case, it's just a subspace of the entire Hamiltonian. So you can have strong ETH violation with respect to Krylov subspaces. You can also have weak ETH violation. So in the model that we study at half filling, there are these spin subspaces. So if I consider Krylov subspaces generated by a product state which consists only of spins, so I don't allow any charges. Because the spins are allowed to move freely, you just get the XX model on L over 2 sites. So this is even more trivial than being integrable. It's just a free fermionic system. And starting from this, you can actually consider an entire tower of integrable subspaces analytically. These are not all of them, but you can just embed dipoles into these spin subspaces and argue that those are also free fermion models, but just on smaller system sizes. And so then you have systems that can violate strong ETH. There are these integrable subspaces which can violate weak ETH. I should point out that there's been recent work by Tom Iadicola where they found subspaces which are beta ansatz integrable and not just free fermions. So you can have even more non-trivial behavior. And then, of course, you can have non-integrable subspaces. So if you consider a subspace that consists of spins and then a single plus charge and a single minus charge separated by some arbitrary number of spins, there needs to be at least one spin in the middle, but otherwise arbitrary, one or any number in the middle. And then this generates a non-integrable Krylov subspace. And we tested that by looking at level statistics within the subspace, which is Wigner-Dyson and not Poisson. And then it also satisfies diagonal ETH. And so this pair hopping model gives an example of a model which is sort of semi-integrable, which has both ergodic and non-ergodic subspaces. And it takes the following form. So there's these finite dimensional subspaces, there's some non-integrable subspaces and some integrable subspaces. And any initial product state will never thermalize with respect to the full Hilbert space, so it obviously violates strong ETH. And this sort of gives a new ETH principle for systems with Hilbert space fracture, where ETH or its absence only holds within each subspace, and it's not really well defined even within a symmetry sector. You have to define it with respect to a given subspace. Okay. And one sort of interesting consequence of this Hilbert space fracture is that you can get thermalization within sort of within a subspace. So for example, if you start with an initial state that has a single charge in a spin background, and you look at its late time dynamics, you find that the late time dynamics matches the infinite temperature expectation value, for example, of charge, but restricted to that subspace. So again, the system is thermalizing, it's just thermalizing with respect to a highly constrained subspace. And so because of that, the charge never relaxes to a uniform distribution. And you see this sort of peak, you see a memory of the initial condition. So I started with charge in the middle site and no charge anywhere. And even at late times, the system remembers that there was a charge sitting at the initial time. Okay. Just to quickly comment on the experimental relevance of this model, as I said, you can get this model by starting from the interacting 1A Stocker block problem and take the limit of an infinitely strong electric field. Of course, the center of mass is only conserved exactly in the limit that E over J is infinite, but you can do a little bit better than that and say that, you know, up to sort of exponentially long time scales, you get pre-thermal behavior. And so up to a time scale exponential E over J, the center of mass is effectively conserved. But even up to that time scale, you'll start generating longer range dipole moment conserving terms at sort of polynomially long time scales. And so this minimal model that we studied isn't quite, it would only really be relevant in extremely large E over J. But at shorter time scales or at smaller E over J, you would get terms that still preserve dipole moment, but are not the minimal center of mass conserving term. Nonetheless, you expect that there'll be some frozen states which remain frozen up to some polynomially long time scale, and then other states might relax to a uniform density profile. And it's been suggested that this happens subdiffusively, and there's been an experiment in Wasim Bakar's lab in a two-dimensional model, which also seems to agree with the subdiffusive behavior. Okay, so just to summarize, I think I'm running out of time. Okay. In this model, we can make rigorous statements about eigenstates, which are in the middle of the spectrum. This is sort of a physical, experimentally relevant system, which shows